NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we learn a powerful rule for nested radicals, see a clean proof, and practice with multiple examples so it feels intuitive. Theorem: if the radicals are defined, the mth root of the nth root of A equals the mnth root of A. In words, the indices multiply. Proof: rewrite each radical as a fractional exponent. The nth root of A is A to the 1 over n. Then taking the mth root raises that to the power 1 over m, multiply exponents to get 1 over mn, convert back to a single radical with index mn. Quick example: the cube root of the square root of 2 becomes a single radical. Multiply 3 and 2 to get 6. So this equals the sixth root of 2. Note, when you have several nested radicals with different indices, you still multiply all indices. Here are two illustrations. Special pattern: if it appears inside north repeated square roots. In this video, we will simplify two nested radicals step by step. Example: we will simplify the 15th root of the cube root of A to the 9th, and the square root of 2 times the square root of 2 times the square root of 2. Let's start with the first expression. We will use the rule: the mth root of the nth root of x equals the mnth root of x. Apply the rule to combine the two radicals. That gives the 45th root of A to the 9th. Factor the root index 45 as 9 times 5. A to the 9th under a 9th root is A, so the result becomes the 5th root of A. Now, for the second expression, we will simplify the chain of square roots. A helpful perspective is to convert square roots into exponents. The square root of x equals x to the 1/2. Start from the inside. The square root of 2 equals 2 to the 1/2. Then 2 times that inside a square root is 2 times 2 to the 1/2. Taking the outer square root raises it to the 1/2 again. Carefully combine exponents. Inside becomes 2 to the 3/2, and its square root becomes 2 to the 3/4. Multiply by the leading 2 inside the last square root to get 2 to the 1 times 2 to the 3/4 equals 2 to the 7/4. Finally, taking the outer square root gives 2 to the 7/8. This is equivalent to the 8th root of 128. Therefore, our final simplified results are the 15th root of the cube root of A to the 9th equals the 5th root of A, and the square root of 2 times the square root of 2 times the square root of 2 equals 2 to the 7/8, which is also the 8th root of 128. In this example, we will simplify the expression left parenthesis square root of square root of square root of 4 right parenthesis raised to the 4th power. Step 1. Combine two nested square roots using the rule: mth root of the nth root of A equals the m times nth root of A. We compress the innermost two square roots into a 4th root. Step 2. Apply the power of a radical rule. The nth root of A, all raised to the m, equals the nth root of A to the m. We move the 4th power inside the outer square root. Step 3. The 4th root of 4 raised to the 4th power is 4. Therefore, the entire expression becomes the square root of 4. Step 4. The square root of 4 equals 2. That is our final answer. Our target expression is the cube root of the square root of 2 times square root of 2, all raised to the 12th power. Step 1. Compose the outer cube root with the inner square root. Multiply the indices 3 times 2 to get a 6th root. Now apply the rule. Step 2. Move the leading factor 2 into the 6th root. A factor outside an nth root can be moved inside by raising it to the power n. Step 3. Interpret the expression as a single power. The 6th root of the square root of 8 is 8 to the 1 over 12. Raising that to the 12th power gives 8. Final value, for example 1, is 8. Example: we will simplify the expression cube root of, open parenthesis, square root of 5 times square root of 2, close parenthesis, raised to the 4th power. We'll move step by step, showing the radical rules we use along the way. Step 1. Rewrite 5 times the square root of 2 as a single square root. Since 5 times the square root of 2 equals the square root of 50, we can write it as the square root of 5 squared times 2. That makes the inside a square root of a square root. Step 2. A square root of a square root is a 4th root. In symbols, the mth root of the nth root of a equals the mnth root of a. Here, m and n are both 2, so the product is 4. Step 3. A root raised to a power can move the power inside the root. We use the rule, the nth root of a all to the m equals the nth root of a to the m. Inside we now have a fourth root of something to the fourth power. These cancel, leaving just the radicand. So the whole thing becomes the cube root of 5 squared times 2. Finally, multiply 5 squared times 2, which is 25 times 2 equals 50. So our simplified result is the cube root of 50. Here is the example, and the expression will simplify. Step 1. Use the nested radical multiplication rule. The mth root of the nth root of a equals the m times nth root of a. We'll apply this repeatedly from the innermost radical outward. Step 2. Combine the indices of the nested radicals by multiplying them. 5 times 4 times 3 times 2 in the index. Step 3. Replace the product in the index by 120. Step 4. A helpful fact. The nth root of a to the k is a to the k over n. Apply that here to get 4 to the 60 over 120, which simplifies to 4 to the 1/2. Step 5. 4 to the 1/2 is the square root of 4, and the square root of 4 equals 2. Method A uses exponents. Define a 1 as the square root of 2. Then recursively define a sub n plus 1 equals the square root of 2 times a sub n. Let's compute the first few terms and watch the exponent approach 1 from below. Notice the pattern. The exponents are 1/2, 3/4, 7/8, 15/16, and 31 over 32. That means the entire nested radical inside the parentheses equals 2 to the power 31 over 32. Finally, raising this to the 32 power multiplies the exponent by 32, giving 2 to the power 31. Method B mirrors the classic step change shown in many worked solutions. We repeatedly convert the outer square root into a higher index root, while bundling a perfect square inside at each stage. We move from a 4th root to an 8th root, then 16th, then 32nd, each time keeping the expression equivalent. At the end, we have the 32nd root of 2 to the power 31, and raising to the 32 gives 2 to the power 31. Here is the expression. We have, open parenthesis, the cube root of the 5th root of a to the 5th times a close parenthesis, all raised to the 15th power. First, we will fuse the cube root and 5th root into a single root by multiplying their indices. The rule is the rth root of the sth root of x equals the rsth root of x. We multiply the indices 3 and 5 to get 15. Now, apply it to the inside. After combining the roots, we get the 15th root of a to the 5th times and still raised to the 15th power. Next, we will simplify the radicand by combining like bases. Inside the radical, a to the 5th times a to the 1st equals a to the 6th. Replace the product by a to the 6th. Now we have the 15th root of a to the 6th raised to the 15th power. We will now use the inverse relationship between an nth root and the nth power. The rule says the nth root of x, all raised to the nth power, simplifies to x. Applying this with n equals 15, we simply get the radicand. Therefore, the simplified result is a to the 6th. Our plan will be compress the stacked roots into a single equivalent root, then rewrite the inside as a single power of 2, and finally use exponent rules. Step 1. Combine the stacked roots. When roots are nested, their indices multiply. Here the indices are 2 from the square root, 4 from the 4th root, and 3 from the cube root. 2 times 4 times 3 equals 24. So the entire nested radical is the 24th root of 2 times square root of 2. Step 2. Rewrite the inside as a single power of 2. 2 times the square root of 2 equals 2 to the 3/2. Therefore, the expression becomes the 24th root of 2 to the 3/2. A useful equivalent form is to put the exponent on 2 outside the radical. That equals the 48th root of 2 cubed. Step 3. Raise a radical to a power by moving the power inside. In general, the nth root of x to the k power equals the nth root of x raised to the k. So we obtain the 48th root of 2 to the 3 times 72. Step 4. Simplify the exponent. 3 times 72 equals 216. So we have the 48th root of 2 to the 216. Now reduce the radical by dividing the exponent by the index. 216 over 48 equals 9 halves. Thus it becomes the square root of 2 to the 9th. Factor 2 to the 9th as 2 to the 8th times 2. The square root of 2 to the 8th is 2 to the 4th, leaving a square root of 2. Therefore, the expression simplifies to 16 times the square root of 2. Example: we will solve 2 nested radical problems step by step. First, the infinite alternating radical with a and b positive. Second, a repeated radical built from the absolute value of x. Part A. Let x be equal to the infinite radical. Because the pattern inside repeats, we will square to peel off one layer. Square both sides. The part under the radical that repeats is the same as x. That turns x squared into a times the square root of b times x. Square again to remove the remaining square root. We get x to the 4th equals a squared times b times x. Now solve for x. Because a and b are positive, x must be positive. Divide by x, then take the cube root. Part B. Consider an n-level nested radical that ends with the square root of x squared. We will show it equals the absolute value of x for any positive integer, n. Start from the inside. The square root of x squared equals the absolute value of x. That means the innermost block becomes absolute x. Now, notice a fixed point property. If a quantity y equals the square root of absolute x times y, and y equals absolute x, the equality holds. Therefore, each outer layer preserves the value absolute x. Repeating n times still gives absolute x. First expression, the 4th root of a squared b squared. Then we will repeat the exact same algorithm for the 4th root of a squared over b squared. Step 1. Apply the product property of radicals. Step 2. Rewrite each 4th root as a square root of a square root. Step 3. Take the square root of a square, which becomes absolute value, and keep the outer square root. Now, we repeat the same 3 moves for the quotient. Step 1. Quotient property of radicals. Step 2. Convert each 4th root to a nested square root. Step 3. Simplify the inner square roots to absolute values. Example: we will find for which real values of x the nested radical is defined. The key idea is to compress the stack of radicals into a single root, then use the rule for even indices. Here is the expression. Our goal is to determine for which x this is a real number. Step 1. Combine the nested radicals. The rule is the ath root of the bth root of m equals the a times bth root of m. Apply this repeatedly to 7, 3, 4, and 5. The product 7 times 3 times 4 times 5 equals 420. So the whole expression becomes the 420th root of x cubed minus 8. Step 2. Because the index 420 is even, the radicand must be non-negative. Even index means the inside must be greater than or equal to 0. Therefore, x cubed minus 8 is greater than or equal to 0. Step 3. Solve the inequality. Add 8 to both sides to isolate the cube. Now take the cube root, which preserves the direction because the cube function is increasing. We get x greater than or equal to 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.